Hi, welcome to this lesson on number patterns, sigma notations. Let's have a look at the second summation formula that you'll find on a formula sheet. So it's given by this formula here. The sum from I equals 1 to n of just the term I is equals to n times n plus 1 all divided by 2. So where does this formula come from and why does it work? Well, if we look at this summation, okay, the general term here, ti, is just simply given by I. So you're adding from I equals 1 to n. So what does this sequence look like? We'll expand it on the next slide, but I'll just give you a quick look now. So that means from I equals 1, you start at 1, plus I equals 2, the next term is 2, plus I equals 3, the next term is 3, all the way up to the last term, which is n. So that is what that expansion of that summation looks like. But the general term is an arithmetic sequence. That is the key here to showing that why this summation formula actually works. The first term a is equals to 1 here. And the common difference here is also d equals 1 because you're just adding 1 to get to the next term in terms of the sequence. So this is the sequence here, 1, 2, 3, 4, 5, all the way up to n. It would stop at n if you are adding up n terms. So we could either use the first or the second formula for an arithmetic series as follows to show that this formula is actually true. So the first formula of an arithmetic series says that the sum of the first n terms, which is given by this summation notation, was n over 2 times 2a plus n minus 1 times d. That was the first formula for an arithmetic series that we learned. Well, we know what n is. It's just n. We're adding up n terms. We know that our starting term a is 1, and we know that our constant difference term d equals 1 as well. So if you substitute 1 and 1 in there, 2 times 1 is 2. N minus 1, so if you distribute out, n times 1 is just n, and minus 1 times 1 is just minus 1. 2 minus 1 leaves you with just 1, and you have a plus n there. So it's n over 2 into n plus 1, which can be rewritten as n times n plus 1 in the numerator, all divided by 2 in the denominator. So that is the mathematical proof of showing why that formula on your formula sheet actually works. We can also use the second formula of an arithmetic series to show that it's true. The sum from I equals 1 to n of the general term I is the same thing as saying n over 2 times the first term a, which is 1, and the last term l, which is your n, right? Because your sequence goes as follows. It's 1, 2, 3, all the way up to n. N is your last term because you kept adding plus 1. So if I put that in there, I get 1 plus n, but addition is commutative, so I can rewrite that as n plus 1. So I have n over 2 times n plus 1, and I can rewrite that as n times n plus 1 all over 2. And that is the exact same result that we come to expect. Okay, so that is where that second formula on your formula sheet is derived from. It is just summing up the arithmetic sequence with the first term of 1 and a common difference of 1. So whenever you are given some sort of a summation problem, where you end up seeing that you can sum, let's say, for example, k equals 1 to m of k, this is the same thing, right? It just looks different in terms of its notation, but it's just saying start at k equals 1, which is 1, then go to the next one, 2, 3, all the way up to m. So what does that mean? It means that instead of n here, because this n here in the formula just represents the upper bound. Our upper bound is m, so it's m into m plus 1 all over 2. So the end result formula only depends on what your upper bound is and must rely that you are starting from the first term, which in this case is 1. So if you're adding up 1 plus 2 plus 3 all the way up to some upper bound number, you can just replace that upper bound in the formula with whatever letter is given there. In this case, here it was m. Okay, so that is where the second summation formula is derived from. I'll see you in the next one.